Hey everyone, welcome to The Explainer. I'm thrilled you're here because today we are jumping right in to decode the true impact of artificial intelligence on medical imaging. If you've ever waited anxiously for the results of an X-ray or an MRI, this absolutely matters to you. We hear so much hype about AI these days, but we're going to break down exactly what the research says about how this tech is fundamentally rewiring the way we detect, characterize, and monitor diseases, especially when it comes to cancer.
Okay, let's set the stage with a statistic that is honestly just shocking. Imagine looking at a complex, highly detailed medical image. Now imagine you have to interpret it completely accurately in just 3 to 4 seconds. Well, according to the data, to keep up with current workload demands, an average radiologist sometimes has to interpret a scan at exactly that blistering pace, all throughout an 8-hour workday.
So, to demystify this whole situation and figure out how we fix that insane pressure on our doctors, here's our roadmap. We'll start with the radiologist dilemma, look at how AI learns to see, examine how it's transforming cancer care, dive into a massive hurdle called the black box problem, and finally, map out the future of radiology.
Let's hit part 1, the radiologist's dilemma, and the reality of just being totally overwhelmed by data. This is really the inciting incident that makes AI not just some fun concept, but an absolute clinical necessity.
Here's the deal. Medical imaging data is exploding at a rate that completely outpaces the number of trained human readers we have. Couple that massive data growth with declining imaging reimbursements, and healthcare providers are essentially forced to compensate by pushing for higher and higher productivity. But radiology relies heavily on visual perception and really complex decision-making under uncertainty. When you force a human brain to do that under extreme time constraints, subjective human errors aren't just a possibility, they are absolutely inevitable. The current system is pushed to its absolute limit.
Which brings us to the solution in part 2, how AI learns to see. We are essentially shifting radiology from a perceptual, subjective craft to a computable, mathematical domain.
Think about the sharp contrast between human methods and AI. Human radiologists generally rely on qualitative reasoning, right? They use years of education, past experience, and their gut understanding of what a healthy scan looks like to spot abnormalities. But that can be pretty subjective. Artificial intelligence, on the other hand, excels at delivering quantitative, automated assessments. It never gets tired, and it can recognize incredibly complex microscopic data patterns across thousands of images in a way the human eye literally wasn't built for.
Now, what's really wild about this transition is how massive a leap AI has taken recently. Look at the older, traditional AI approach. It actually required human experts to manually program specific mathematical equations just to define things like a tumor's texture or shape. But contrast that with the newer approach, deep learning, specifically convolutional neural networks, or CNNs. This new method doesn't need humans to handcraft those rules at all. It uses hidden layers to automatically extract and aggregate those features straight from the raw pixels.
So the absolutely crucial takeaway here is that deep learning figures out the best features automatically from the raw data. You don't have to explicitly program it. Because of this, it's incredibly adaptable to all sorts of different imaging. Whether it's a CT scan, a PET scan, or an MRI, it learns directly by navigating the data space. It essentially teaches itself exactly what to look for.
All right, part 3, transforming cancer care. Let's look at how this actually plays out in the real world and revolutionizes the clinical radiology workflow.
We can break the core radiographic workflow in oncology down into 3 consecutive essential steps: detection, characterization, and monitoring. And AI is making massive waves across the board here.
Step 1 is detection. This is finding the needle in the haystack. For identifying tiny pulmonary nodules in lung cancer screenings or spotting subtle lesions in mammograms, deep learning computer vision algorithms aren't just fast anymore. They are matching human readers and completely outperforming older computer-aided systems at finding the actual lesions. But once you find it, you've got to know what it is. That's step 2, characterization. And this brilliantly illustrates AI's power. It can automatically segment the exact boundary of diseased tissue, which is notoriously difficult to do by hand. Then, it uses quantitative biomarkers to analyze the internal texture and sphericity to help diagnose if a tumor is benign or malignant. This is huge for helping doctors accurately stage the cancer.
Finally, step 3 is monitoring. To know if a cancer treatment is actually working, doctors have to compare scans over time. But normal human inconsistency and poor image alignment make this super tough. Deep learning dramatically improves image registration, which means perfectly aligning the tissues across multiple scans, so doctors can reliably track the most subtle variations in a tumor's size, shape, and internal structure. But look, just as we might think AI is a flawless magic bullet ready to fix healthcare overnight, we hit a wall. Part 4, the black box problem. We really need to talk about the massive hurdles standing in the way of using this in actual clinics.
The biggest of these is what researchers call the black box problem. Because of how deep neural networks are structured, with hundreds of thousands of hidden nodes, they are completely opaque. We feed the AI data, and it gives us an incredibly accurate diagnosis, but we can't easily interrogate the neural network to explain why it made that specific decision. It's kind of like a genius student who always gets the right answer on a math test, but absolutely refuses to show their work. The logic is hidden. And when a system lacks transparency, it is incredibly hard to troubleshoot failures or predict when it might break down across different patient demographics. So, summarizing the major roadblocks here. First, training these models requires expensively curated medical data that has to be labeled by human experts. Then, you've got the uninterpretable black box neural networks we just talked about. This poses huge regulatory challenges for groups like the FDA because these algorithms actually evolve and change over time as they process more data. Plus, we face strict patient privacy risks under HIPAA. Although a really fascinating proposed solution to that privacy issue is something called federated learning. It's a decentralized approach where the AI model travels to the individual hospitals to learn locally, rather than moving all your sensitive private patient data to some vulnerable central server.
Which brings us to Part 5, the future of radiology. It's time to answer the absolute elephant in the room. Are machines going to replace doctors?
Take a look at this graph, mapping the trajectory of AI versus human intelligence. It's a fascinating trend. The bottom line represents AI. The top represents humans. While AI is rapidly rocketing past human performance in narrow, highly specific tasks, like recognizing an image pattern, it completely lacks top-down, real-world context. The general consensus is that as we integrate these tools, human intelligence and our overall capabilities will actually elevate as we learn alongside the AI.
The researchers are completely unambiguous about this. The resounding takeaway is that AI will not replace human doctors anytime in the near or distant future. Instead, the radiologist's role is just going to expand. The machine handles the tedious, quantitative pixel crunching, while the human acts as the critical overseer, bringing high-level medical context and, actual empathy to the patient's care.
But as we build this interconnected web of AI tools, I want to leave you with one final, highly provocative thought from the research. As this technology integrates seamlessly into hospitals and starts making autonomous diagnostic suggestions, who takes the blame if the machine gets it wrong? From a legal and ethical standpoint, who is ultimately responsible? It's a huge question we're going to have to answer very soon. Thanks so much for joining me on this explainer. Keep asking questions, and I'll see you next time.